The statement of the numerical is: draw the circle diagram for a 5.5 kilowatt 400 volt 3 phase 50 hertz 4 pole slippering induction motor from the test data given below. I'll write down the given data here. It's a 5.5 kilowatt induction motor. $400 3 phase 50 hertz 4 pole slippering induction motor. And then they have given the no load test results and block rotor test results. No load test results are 400 volts, six amperes, 0.085 power factor lagging. And for blocked rotor test, the data given is 100 volt, 10 ampere, 12 ampere, and 700 watts. And they have asked, and also they have given the ratio of primary to secondary turns is 2.6. And also stator resistance per phase is 0.67. And that of rotor is 0.18. 0.18 ohms. Now they have asked us to calculate the first point full load current, second point full load slip, third point ratio of maximum torque to full load torque, maximum torque to full load torque, fourth point starting torque. Yes, these are the points to be calculated. Okay. Now they have given us the no load test results and block rotor test, and they have also given the rating of the induction motor. Now need to calculate the first thing to be calculated. Solution. First thing to be calculated here is Here they have given V naught, I naught, and cos phi naught. V naught is 400 volts, I naught is 6 amperes, and cos phi naught is 0.085. And here it is VSC, ISC, and they have given WSC. So calculating cos phi SC should calculate cos phi SC, as well as we should be calculating ISN and WSN. Okay. Now cos phi naught is, first thing, from the no load test results, cos phi naught is 0.085. Hence, phi naught will be equal to 85.12 degrees. Similarly, they have given WSC as 700 watts. So we know that WSC is also equal to root 3 VSC, ISC, and cos phi SC. So directly I can calculate cos phi SC 700 divided by root 3 into 100 into 12. 100 into 12. It results in 70.3 degrees. 70.3 degrees. Now after this, I should be calculating ISN, which is equal to ISC into VL divided by VSC. Now, ISC is known that it is 12 amperes into VL is 400 volts, VSC is 100 volts. So here ISN will be 48 amperes. ISN is nothing but short circuit current under normal voltage. Here, again I repeat, here this is only no load test results. At 400 volts, if the motor is kept under no load condition, it will be taking hardly 6 amperes. Now under block rotor test, we are applying reduced voltage. We are applying reduced voltage, and that time we are circulating the rated current. So here under reduced voltage it is 12 ampere. Now we want to see what will be the current if the rated voltage is applied. If the rated voltage is applied, this will go up to 48 amperes. Now we'll calculate WSN. WSN is equal to, we have the formula, that is WSC into ISN divided by ISC whole square, which is equal to, I'll write down the numbers here. WSC is given as 700 into ISN is 48 divided by ISC is 12 square. So the total WSN is 11,200 watts. Okay. After this, we now know the ISN, we know WSN. This much is sufficient to start plotting the graph. Okay. Selecting proper current scale, we can start it. Now this is the graph page here. This is the graph page here. Since the actual graph page will be of hardly 20 to 30 centimeters, select the proper scale to accommodate this 48 amperes ISN into the graph page. Now this is voltage scale, this is current scale. Now to accommodate 48 amperes in the graph page, let me take the current scale as let me take the current scale as 1 centimeter is equal to 3 amperes. 1 centimeter is equal to 3 amperes. If I do that, then first I should be drawing the I naught. The I naught from the point O. O is origin here. Now I should be drawing the I naught, which is 6 amperes, but as from the current scale, that will be 6 amperes, and it is 1 centimeter is equal to 3 amperes. So it is 2 centimeters. 2 centimeters, and we also know that the cos phi naught is given here, and we have also calculated the phi naught, that is 85.12. So making an angle of 85.12 from the voltage axis, I should be drawing I naught for 2 centimeters. So this is 2 centimeter line making an angle of 85.12 degrees. Now this is O dash. O dash. Now from this point I should be drawing a horizontal line to the horizontal axis. Okay. Now after this I should be drawing this ISN. ISN once again from the starting point or the origin, that is 48 amperes. Now this is in amperes, convert this into centimeters, that is per using the current scale. 1 centimeter is equal to 3 amperes, that means ISN 48 amperes divided by 3, 16. So starting from the point O, draw a line of 16 centimeters with the angle 70.3. Once again, cos phi SC, the calculated answer is 0.3367. Hence, phi SC is cos inverse of this, which is equal to 70.3 degrees. Okay. Now, phi SC is the angle between V and ISN. So, draw the line from the point O with an angle of 70.3 degrees with the V, which is a 16 centimeter line. 70.3 approximately, I am taking it here. It's a 16 centimeter line. 16 centimeter line. I'm naming this line as point A, and this is making an angle of 70.3 degrees. 70.3 degrees. Okay. Now, as from the procedure, join O dash and A. Join O dash and A like this. Okay. And this is called as output line. This line, O dash A line, is called as output line. Now, draw a bisector to this O dash A. Draw a bisector to this O dash A. This is the point. If I draw a perpendicular line to this O dash, or using bisector also we can bisect this, and by extending the line till this horizontal line, I have got this point, name it as point C. Now keeping the point C as the center and O dash C as the radius, draw a circle, draw a semicircle till it reaches the point B on the horizontal line. Okay, now I'm naming this point as point B. Okay, and then from the point A, draw a vertical line draw a vertical down line till it reaches the horizontal axis, and this point, name it as point D. This is point D. Now this is about drawing the circle diagram. Now after this, we can start calculating the points which they have asked. That is, they have asked us to calculate full load current, full load slip, maximum torque, ratio of max torque to full load torque, and then starting torque. Now here, we should, to have this maximum torque to full load torque ratio, I should be anyhow marking the point E on this line, and now I'll mark this point as, I'll name this point as point F. Okay, now I should be pointing the E, okay, E on this line, AF line. Okay, now to mark the point E, I should calculate the ratio of AE to AEF, AE to EF, and since it is known that it is a slippering induction motor, we know that the ratio AE to EF is R2 dash to R1. We have already seen that. Okay, we have already derived that for the slippering induction motor, the ratio of AE to EF is equal to R2 dash to R1, and we also know that R2 dash is equal to R2 by K square. Okay, now we know that the value of R2 is 0.18, sorry, this ratio K is 1 upon 2.6. Okay, because they have given us stator to rotor turns ratio. Okay, and primary to secondary turns ratio is 2.6, but we always consider turns ratio of rotor to stator is 1 upon 2.6. Okay, now here R2 dash is R2 upon K square. We know the R2 that it is 0.18 divided by K is 1 upon 2.6 whole square. So 0.18 by 1 upon 2.6 whole square will be 1.2168. R2 dash is in ohms. Okay, now R2 dash is calculated, so now we can check out the ratio of AE to EF. AE to EF, now I can write it as 1.2168 divided by 0.68. R1 is 0.67, sorry. Okay, since this ratio, both are numbers, we can finally calculate that it is equal to 1.8161. This AE by EF is giving us the ratio of rotor copper loss to stator copper loss. So here I can write it as rotor copper loss to stator copper loss. This ratio is giving us 1.8161 is giving us ratio of rotor copper loss to stator copper loss. Now we also can calculate the total AF length. Okay, now we know that this AF is giving us the total copper loss. So here I can write that AF is equal to AE plus EF. I know that. Okay, AE plus EF. This because anyhow I'm going to mark the point E on this line only. So AE plus EF is equal to AF. Now I can write that AE plus here we know that AF is equal to AE plus EF is equal to, once again keeping the same AE, EF. Now if I rewrite this equation, EF is equal to AE divided by 1.8161. Take this on to the right hand side, shift this to left hand side. So EF, I can write it as AE by 1.8161. Here, shifting this EF to AE divided by 1.8161, I have written the equation. Now AF again, now this equals to 1.5506 AE. This results in 1.55 times of AE. Now I can take AE as AF divided by 1.5506. Now this is nothing but AE by EF 0. AE by AF is equal to 1 upon 1.5506 is equal to 0.644. That means I have just shifted this AF this side, so 1 upon 1.5506 is equal to 0.644. Now that means the ratio of AE to AF, AE to AF is equal to 0.644. That means AE is 64% of AF. Okay, I'll write down here AE is equal to 0.644 times of AF. Okay, AE is 0. The point E will be here at the 64% of this entire length. Okay, now here we know that the total length of AF should be noted. The length of AF, I have got it as length of AF, I have got it as 5.45 centimeter, 5.45 centimeters. Now we know that AE is 0.644 times of AF. So length of AE is 0.644 times of 5.45. That is equal to 3.5 centimeters. 3.5 centimeters. Now the length of AE we have got. The length of AE we have got it as 3.5 centimeters. It will be somewhere here. So marking this point as E. Now I can join O dash and E. This length is 3.5 centimeters. Okay, this is 3.5 centimeters. Now length of AE is known, so easily you can calculate the length of EF, which is equal to 5.45 minus 3.5. Okay, now we should also be calculating after this. Now they have given the rating of the machine as 5.5 kilowatts. It's a 5.5 kilowatt machine. Okay. Now here this entire line AD, which is describing, which is giving us the loss. AD is completely lost. This is rotor copper loss, this is stator copper loss, this is constant loss. Now if I have to show the output 5.5 kilowatt, I should be extending the line over the point A, from the point A vertically upside. Okay. Now for that I should be calculating first the power scale, then extend the line for 5.5 kilowatts corresponding to the power scale. Now first of all we should be calculating the power scale. Now the power scale is equal to the length of first WSN divided by length of AD. Okay, WSN we have calculated that it is 11,200 watts whole divided by length of AD. Length of AD is equal to 5.55 centimeters. Now this results in 2018.01 watts per centimeter. Now this is power scale. This is power scale. Okay. Now I want to convert this 5.5 kilowatt into centimeter. So AA dash, the length of AA dash, I want to put this in the graph page. So I should be converting this into centimeters. So, and I am doing that over the point A vertically upwards. So that line should be of how many centimeters? We are going to calculate that now. Okay. So length of AA dash I can give it by doing 5.5 kilowatt divided by power scale, that is 2018.01 watts per centimeter. Okay, kilowatts divided by watts per centimeter. So this will be in terms of centimeters. If I do 5.5K divided by 2018.01, it will result in 2.73 centimeters. So that means I should be extending the line from the point A vertically upwards for 2.73 centimeters. Now this is the point A dash. This length is equal to 2.73 centimeters. Okay. Now to get the actual operating point, I should be drawing a parallel line from the point A dash, which is, and it should cut the circle diagram like this, and this point is called as the actual operating point. Okay. Now that is the point here, and I am naming that point as point P, and draw a vertical downwards line till it reaches the x-axis. Now this point is point Q. The line where it is intersecting with the output line is named as Q, and this is R, and this is S. Okay, Q, R and S. and the point intersection with the horizontal axis is T. Okay, Q, R, S and T. Okay, Q, R, S and T. Now to calculate the first point, that is full load current, I should be drawing a line. I should be joining O and P. Join O and P, measure the length OP. Okay, this is the first point I'm calculating here. Full load current, which is equal to length of OP into current scale. It is the length of OP into the current scale. I have got it as 4.5 centimeters into my current scale. Here it is 3 amperes per centimeter. 3 amperes per centimeter. So it will be 13.5 amperes. Now the second point they had asked us to calculate was full load slip. Full load slip is QR divided by PR. QR divided by PR. Okay, that is giving us the full load slip, that is output divided by rotor copper loss 2. The total rotor input is nothing but full load slip, which is equal to QR by PR. Now QR is 0.2 centimeter divided by the length of PR is 2.9 centimeters. This results in 0.068 or else 6.8%. That is full load slip. Now the next point, is full maximum torque to full load torque, T max to TFL. Now to get the maximum torque, this is the torque line. Now to get the maximum torque, I should be drawing a parallel line to this torque line, which should also be tangent to the circle. Okay, so this is the line parallel to the torque line and which is also tangent to the circle. Now if I get the point here, draw a vertically downward line till it reaches the torque line. Okay, now I am naming that point as point J, and this point where it intersects the torque line, I am naming that as K. So this length JK will give us the maximum torque. Okay, that is about maximum torque. And length PR, okay, which is the output, the length PR is the actual output. Output is nothing but in terms of torque. So this is the full load torque. This is the operating point for the full load condition. So the length PR is giving us the full load torque. Okay. So since we are finding out the maximum torque to full load torque ratio, no need to convert them into watts or Newton meters. Directly let them be in the centimeters only. We can calculate the ratio. Now if I take out the length of JK, I'll write it down here, length of JK to length of PR. So length of JK, I have got it as 5.7 centimeters, 5.7 centimeters, and the length of PR, I have got it as 2.9 centimeters. So the ratio is equal to 1.965. The ratio of maximum torque to full load torque is 1.965. Now, the fourth point they had asked us to calculate was starting torque, that is T start. T start, for that we have the equation, that is length of AE. AE, this is rotor copper loss. This also gives us the starting torque. Okay. Now the length of AE is 3.5 centimeters, but I want the torque in terms of Newton meters. So to convert that into Newton meters, first thing I should be doing is convert this 3.5 centimeters into wattage. We know the power scale, so T start, I can write it as 3.5 centimeters into, we know the power scale, that it is 2018.01 watts per centimeter. So centimeter will get cancelled, and hence it is equal to 7063.035 synchronous watts. Starting torque is in terms of watts now. Okay, but we want the torque in terms of Newton meter. So to convert this into Newton meter, we know the equation that P is equal to omega T, where T is the torque. So where T is the torque. So torque is equal to P divided by omega, where omega is equal to 2 pi N S by 60. Capital N, 2 pi Ns by 60. Ns is synchronous speed of the motor. Now we don't know the synchronous speed, so first calculate Ns. Ns is equal to 2 pi, Ns is equal to, 120 F divided by P. 120 F divided by P. 120 into frequency, they had given it as 50, and number of poles they had mentioned as 4. So it is equal to 1500 RPM. Okay. Now if I calculate the torque, starting torque, T start, in terms of Newton meter, it is synchronous watts, that is 7063.035 whole divided by 2 pi Ns by 60. 2 pi Ns is 1500 divided by 60. This is omega. T is equal to P by omega. T is equal to P by omega. P, it is although the torque, but it is in terms of watts, so I am taking it as P. Okay. So if I do this, I'll be getting it as 44.96 Newton meter. 44.96 Newton meter. Okay. This is the solution for the numerical. Okay. Here we have found all the points, that is full load current, full load slip, ratio of maximum torque to full load torque, and then the starting torque. Okay? Hope you people understood the solution.